Hey guys, this video is going to be about understanding moment of inertia, really trying to know what the term is so we can use it appropriately. We're going to define the term and then try to compare it to the perfect physics world where everything's a sphere, in a vacuum, so on and so forth. And then look at the more realistic mass distribution and how that would affect the rotational motion of objects. After all, Physics C class, the calculus-based physics class, is about trying to more realistically model the world with the use of calculus. And then we're going to derive the moment of inertia for some common objects, and hopefully by the end of this you will have a tool through the calculus-physics intersection that will allow you to find the moment of inertia for almost any shape. So the whole way we presented this in the beginning was I asked you to find torque as a function of angular acceleration. And the difficulty in the lab was figuring out how to actually measure or calculate from measurements the torque. And that will be a challenge that we'll figure out coming up pretty soon. The angular acceleration was measured from tracking either the angular position versus time or the angular velocity as a function of time, and seeing that the angular acceleration was some value each time. From a theoretical derivation we knew that there was a direct relationship, and if you started to graph your data, you saw that already. And this would mean that we have some function like this, right? And we're going to replace the variables torque for y, angular acceleration for x. And the question was, what is this? And that was the main point that this lab that I presented was having you find, is what is the proportionality constant between torque and angular acceleration. And so what we did was we went through a sort of little theoretical description. We said, well, we already know from an alternate experiment that torque is F cross R. And if that's true, then we can write it as F cross R equals this something times alpha. So at that point, let me just move some things around here, have a little more room. Okay, so at that point, we were trying to write force, the translational force, so the net force equals mass, inertial mass, times acceleration. And we know that acceleration is converted into the rotational analog by saying r times alpha. So let's plug this in. So F equals m times r times alpha. Okay. And we know torque, again, if we go back to the torque, is F cross r. So therefore torque will be mr alpha times r, which ultimately becomes mr squared times alpha. So we have this new version of the function, torque equals mr squared alpha. And that mr squared alpha is the function of the graph that we had right over here. Okay, that mr squared alpha, or the mr squared term, is the slope. And so we had sort of pinpointed in the lab that the mass of the rotating object, right, after all, that's what's turning, and the radius at which it's turning, where the force is applied to it, are the two most important variables in figuring out what this proportionality constant is. Now, if we think about comparing force to torque, if force, the net force, right, was the rate of change of momentum of an object, also written as mass times the net acceleration, and we have studied very, very intentionally that mass, inertial mass, which is translational inertia, is an object's ability to resist a linear acceleration. So I'll say that again. An inertial mass, or just mass, for translational inertia, is an object's ability to resist linear acceleration. So it's a resistance to a change in the motion of the object. And what is that? That's the m. Now for rotational inertia, which is this torque equals m or I times alpha, I is what we are kind of unpacking here, this term, right? This is an object's ability to resist a change in rotational acceleration, right? A resist to change in rotational acceleration. And so it's the same basic idea, but now it doesn't only rely on the mass, but it also relies on how the mass is distributed around the axis of rotation. And that's where that circled blue term comes from. So now, going forward, we're going to be able to unpack what this is. So we can make a definition. A moment of inertia is an object's resistance to rotational changes in motion, resistance to rotational acceleration, and it relies on these two variables. And you can kind of see that as you look at your data for the lab. So let's go ahead now and take a look at how would we actually use this to find a moment of inertia. Okay, so we take a look at this function, and we know that this term is really what we're interested in right now. And we're to call that I. For convention's sake, that's what I will be. But it's more than just mr squared, because as we unpack some example problems here in a second, you'll see that objects that have most of their mass near the axis of rotation have smaller rotational inertias than objects with more mass farther from the axis of rotation. And it's clear from this function, right? If I is the resistance to change, then a high I, or a high moment of inertia, will be a greater resistance to angular acceleration change. So when you talk about something having a greater moment of inertia than something else, what you're saying is that thing doesn't want to rotate as easily as something else with a lower moment of inertia. And you can see clearly here, as r increases, I will increase, quadratically in fact. As there's more mass, there will be more moment of inertia, but I think that makes probably a lot of sense, because it would be sort of the same as in the translational sense, that if you have more mass, just more mass, it will be more difficult to rotate. But here really the r is the kicker. And so let's take a look at how to solve what the moment of inertia is for some sort of very simple system. Okay, so I have here an object that is similar to one of the rods that we were rotating in the lab. This has this very sort of negligible mass, a very, very thin rod connecting two masses, and in this case each one is 3 kilograms. The rod is 1.2 meters long, and so we are going to try to find the moment of inertia, rotate it about the center, and then rotate it at one end. And this is what's kind of interesting about moment of inertia, is that when you actually calculate the moment of inertia, it depends on the orientation of the object. Where in translational motion, we always said, well, the mass is the mass, and it doesn't matter what the shape is. We never concerned ourselves with that before, except to find the center of mass. And now we're going to take a sort of closer look. So the idea would be that, well, if I want to find the total moment of inertia, I have to sum up the individual moments of inertia for this sort of shape. And so in this case, I would have 3 kilograms times the location from the center of rotation, which in the first case is going to be 0.6 squared, because I said it was a 1.2 meter long rod. And then I have to add that to the other mass and its location, which would be the same from the center. So we'd have this. And what I'd find is that I would get 2.16 kilogram meter squared. All right, and that would be the moment of inertia for that object. Now, rotating it on one end would be very different. Now, initially I had the axis of rotation right here down the middle, but now I'm going to move that along here. Okay, so let's try to imagine what that would look like. So let me move some of this stuff out the way. Keep that one up top. And so we're going to do the same thing over again and take this now as our axis of rotation. So we're going to say the moment of inertia is equal to the mass of 3 kilograms, that's the one on the left, times now it's 1.2 meters away from the end. That of course is squared. And then I can add the other one just to show you that if we put 3 here, but it's 0 from the end, its mass doesn't even contribute to the whole moment of inertia because it's at the center. And this I had come out to 4.32 kilogram meters squared. So on looking back at this, what's interesting to me is you can tell from then this example by comparing these two what's more important in terms of having a lower moment of inertia. Well, it would be actually the distance distribution of the mass instead of the total mass itself, because you can see at the top there it is much less than the bottom example, and that hopefully is obvious by the fact that the r is squared. Okay, so finding the moment of inertia is as simple as summing all the individual locations of mass from the axis of rotation. So in order to solve these kinds of problems right now, what you would have to do is you would have to find the axis of rotation. That has to be defined first. And once you know that, then figure out the distance of that sort of point mass distribution from the center of mass, and then just do the summation as you've seen here. So there are some practice problems on the PowerPoint that is linked to this video. So take a look at those if you want to do a little more practice. But let's try to get into a more useful sort of stance right now and be able to find something where the mass is not just two blobs at the end of a massless rod, because we don't come across those very often in the real world. Now, it's a decent approximation, but what if the mass is evenly distributed along the length of the rod? And so let's go over to the next slide and try to do that. Okay, so we're going to start with trying to find the moment of inertia of a real rod, not some fake thing. All right, now what we have to consider is that the moment of inertia of any point mass is I equals sum of mr squared, but the rod would have to be considered to be an infinite number of point masses. And so each has to be multiplied by the square of its distance from the axis of rotation. So like I said before, the first thing to do is consider where the axis of rotation is. And I'm going to start by doing it around its center first. So we take a look at that, and we're going to sort of replace some of the ideas of what we have used from calculus to get from this idea, r squared m, or mr squared. So what we're going to do is we're going to break the rod up into many, many small pieces, right? Lots of little point masses. And we're going to have each from its center of rotation. So what I'm going to do is I'm going to rewrite this function. I'm going to say I'm going to break up this object into tiny bits of mass, right? And I'm going to be able to sum all those masses, those little pieces, from wherever to the total mass. And if I do that, I should sum up all the very, very small moments of inertia, because each little mass has its own moment of inertia relative to it, or because of its distance from the axis of rotation. So I'm going to sum all of these together. So this would be our function for the new total moment of inertia, then would be the sum of all the little mini moments of inertia, if you would say. So now let's try to apply the formula to the common shape of the rod. So after picking the axis of rotation, which I've done, I have to consider what would be very important is the density, because that would define how the mass is distributed. And so we're going to do, we'll just consider this to be a completely linear rod that has no other dimension. So we'll say its mass divided by its length, is its linear density. So let's go ahead and see what we have to do here in order to find this. And so we've got to define the distance from the axis of rotation. So I'm going to consider this to be L over 2 and this to be L over 2 as the distance from the center of rotation. In fact, this would have to be negative L over 2, so we have it to be continuous. And so let's take this idea, the density, and say that the mass of the rod is equal to the density times the length, and we are going to use this idea now to break it into very small pieces of mass that have density m over L, total m over total L, right? As we break them into small little segments. So what I've just written here is I've written the value, sort of the value of a very small piece of mass. It's the density times a very small sort of piece, distance, right? And so we're going to take this idea now and we're going to use it here to sort of change the variable of integration from m to r, as you can kind of see. So let's move this up so we have a little more room here. Okay, and we're going to put this into the function, and we're going to say that I is equal to integral r squared m over L dr. And that's going to be integrated from negative L over 2 to L over 2. All right, so quick recheck. We have broken up the rod into tiny little mass pieces. So each has its own tiny little moment of inertia. We're summing all those tiny pieces together. Obviously, the way where the mass would be and what it would be at any position along the rod would be dependent on what its linear density is, which is what you have up in the top right-hand corner. I've solved the linear density for the mass, so mass equals linear density times L, and linear density would actually be a lambda most of the time, so I've just sort of using the rho, so just kind of translate that in your head. Then I said, okay, I want to break it down into tiny pieces of mass, so I have it as dm, and the L would of course break down into very small pieces of position or length, which would be dr. And then I've substituted in for the linear density total m over total L, because we're considering this rod to be a uniformly dense object. Okay, so let's do the integration now. Let me move this up again. All right, so to integrate, we are going to pull out the constant, which would be this. So we're really just integrating the r squared value, which is going to become r cubed over 3. And we're still evaluating that from negative L over 2 to L over 2. All right, and so when we do our substitutions here, okay, so let's integrate this. So at this point, what we're going to do is I would factor out that 1/3 that's going to be in this fraction. So I'd make this m over 3L, and that's going to become L over 2, and that's cubed, minus negative L over 2, also cubed. Sorry, this should be cubed. And that's a cube that I can't really see. And so we're going to get m over 3L times, let's do this, so this would be L cubed over 8 minus negative L cubed over 8. Okay, so we can simplify this. What I would do next is I'd probably factor out that 8 and do m over, what's that, 24L, and then L minus negative L cubed minus negative L cubed would give me 2L cubed, right? And so then next after that, we'll simplify this. L will make this L squared, and the 2 and the 24 would become 1/12 ml squared. And that, if you forgot from the beginning of this long slide, is that the moment of inertia of a rod rotating about its center, if it's uniformly dense, is 1/12 times its mass times its length squared. So that's kind of cool. This is something you should definitely be able to derive again on a test. AP Physics C test has asked people to do this often. So I suggest reviewing this slide. Let's go ahead and try to figure out what its moment of inertia would be if it was rotating around one end. Okay, so we define, remember, our axis of rotation, which we're making along one end. Then we're breaking this up into lots and lots and lots and lots of small little pieces, all at varying distances r. And so we're going to start with our definition, integral r squared dm. We have to consider the density of the object. So if we say the linear density is equal to the mass over the length of the rod, then the total mass of the rod is equal to the linear density times the length. We obviously want to break this into lots of small pieces of mass that we could sum together. The density is going to be m over L, and breaking up into small little pieces would be dr. So we're going to go ahead and change this variable of integration. So this will become I equals integral r squared m over L dr. Okay, and then we will integrate this time from 0 to r, okay, because we're starting along one end. I guess in this case it should actually be 0 to L, not to r. Okay, so let's do this. So we should pull out the constant, I should say. This becomes r cubed over 3, integrated from 0 to L, and then we should be able to do this fairly easily. So we'll have L cubed over 3 minus nothing. Okay, so there we go. And now we can do some simplification. So we get, as you can see, 1/3 times ml squared. And that should be the moment of inertia of a rod that has a uniform density rotating about one end. So the steps, sort of the strategy is define where your axis of rotation is first. Write your definition, right? Then realize that if you understand what that definition is, you're breaking up this rod into very small pieces. So in terms of its density, how much mass is located in each piece will depend on the density. And so we come over here to the side and we do this little sort of side analysis. And that says then that we can change the variable of integration, integrate from the axis of rotation to where we have the end of the rod, and we should get 1/3 ml squared. Okay, there's actually another quick way to do this called the parallel axis theorem, and what that's going to allow you to do is actually use this definition that the moment of inertia of any object about an axis through its center of mass, because that's basically what we've been doing. When you're trying to find where an object's rotated around, you have to find its center of mass first. That's the place, right? So the moment of inertia of any object about an axis through its center of mass is the minimum moment of inertia for an axis in that same direction. So what we basically mean is that the moment of inertia at any axis parallel to the axis through the center of mass will be the following. So the moment of inertia equals the moment of inertia about the center of mass. That would be the rod in the first example we did, rotating around its center of mass, so the center of the rod. And then adding the mass times the distance to the new axis squared. So for example, we have this, right? We find the moment of inertia around the center of mass, okay, which we did, And then any axis parallel to that, so I should write here parallel axis for that moment of inertia. So say I want to get it along the end. This is a parallel axis to the center of mass 1. So I should just be able to take this distance squared times the mass, the point mass of that location, and add the two together. So let's just see if it works, if we get the same thing. We're expecting to get 1/3 ml squared, because that's what we got for the shape rotating about one axis. So what I'm going to do here is say, I already found that it's 1/12 ml squared about the center of mass. So I'm going to add the mass times d squared to get this next value. Okay, so that's going to be the total mass, and then the distance is L/2, and that of course is squared. So really what you're saying here is you're saying that the second term here is the total mass of the object, and its position is located at the center of mass of the object, right? So we're assuming that all the mass is at that point. So if we simplify this, we've got 1/12 ml squared plus 1/4 ml squared, and if we use our find a common denominator for that, we should get 1/3 ml squared. So that's an easier way. If you found the axis of rotation about the center of mass, if you found the moment of inertia about the center of mass axis of rotation, then you can just add the second term that you see is the total mass existing at the center of mass squared the distance to the new parallel axis, and you should be able to do it the same way. That's kind of cool. Okay, next up, we're just going to do one more example. Let's look at a moment of inertia of a very thin ring or loop. And hopefully you can kind of see some parallel of something we've actually already done. Okay, so if we have a ring where all the mass is located at this very sort of infinitely small space along the edges here, it's effectively the same thing as having a massless rod with a mass over here at the end. So really it's the same as a very simple, all the mass is located at the end of the R if it's rotating around its natural center of mass, which would be the center of the ring. So if you have an irregular shape, you first have to find the center of mass, if that's the axis around which it is rotating. Then you would use that now to help you find where the mass is located. But let's say that this is filled in. Okay, so it's completely filled in, and it's evenly distributed. So it has a surface density that is uniform, but of course that's going to affect how it rotates because not all the mass is located at the end. So we'll have our definition here, integral r squared dm. And remember, we've got to change the variable of integration, and that is the m, and we want to make this in terms of the density because that's going to affect where the mass is at every position. So let's write the surface density, we're going to use sigma, is equal to, let's see, it would be the total mass over the area. Okay, so the mass total is going to equal the density times the area. Okay, and so we're going to say dm, small value of mass, is equal to sigma, which is constant in this case, dA. Now dA is derivative of the area, so the derivative of pi r squared, which would give me, so this would be sigma times 2 pi r dr. Alright, so now I know a value of, in terms of r, of a very small piece of mass. So I'm going to come back up here and I'm going to do integral r squared times sigma 2 pi r dr. And I'm going to integrate from the center to r. Alright, and so let's do some simplifications here. This ends up being integral 0 to r, r cubed. And then we've got these constants here, 2 pi sigma, which you can take out front. And we should be good. So I'm going to try to put those over here. So 2 pi and sigma. Those are going to come out front here. And then, so let's integrate this, which is going to be r to the 4th over 4 evaluated from 0 to r. Now I'm leaving out my constants here just because I don't have enough room, and that will help me put everything in. So that's going to really just become r to the 4th over 4 times sigma 2 pi. That's not a 6, but a sigma. Doesn't look like one. And then sigma is a value, so let's move this up here a little bit. Sigma is a value of m over pi r squared. Right, so I'm going to use that. So ultimately I've got here r to the 4th over 4 times m over pi r squared times 2 pi. So we got all of this to simplify out, so I get rid of the pi's. The r squared obviously makes this r squared, and then I can simplify this to 1/2. So I end up with 1/2 mr squared, or r squared m, either way. Okay, so that's the moment of inertia of a solid disk rotating around its center of mass, which is its center. So it's a game of trying to substitute in density. And really, why did I substitute the density back in at the end? Because I could have left it in terms of the density. I did that because I just want to get it in terms of m and any distance to where the mass is located. So that eliminated all that extra stuff. You should be able to derive these with calculus on the test. Now, if I wanted to find out what the moment of inertia was around one end, so if I'm looking from above, we just found it rotating around here for a solid disk, but what if I wanted to find it rotated over here? Well, I could use that parallel axis theorem, which would allow me to take this value that I just found, the rotational inertia around the center of mass, and add the distance r, right, r squared, plus the total mass. And that would add to this 1/2 mr squared, and I would find the new axis of rotation, the new moment of inertia around that new axis of rotation. Now what you can do is compare, what if we had axis of rotation here on the end, we had one here in the middle, or maybe we had one that's perpendicular to both of those. What if it was spinning like that? How would that affect it? So we can actually, there is a perpendicular axis theorem as well, and for any planar objects, so sort of like this, the moment of inertia about an axis perpendicular to the plane is the sum of the moments of inertia of two perpendicular axes through the same point in the plane of the object. Okay, and we'll take a look at this in a later video or in class. But you can figure that out, fairly easily. And so we'll pick up on this and take a look at cylinders and other things. But this video kind of gives you some of the basics of where we started with finding that mr squared was the proportionality constant between torque and alpha, right, the angular acceleration. And we took that idea and we developed it into finding the moment of inertia of an object that is uniformly dense, but is not a point mass located some distance away from the center of rotation. So what you can do is use this now to sort of reanalyze your lab work and see if you get close to the moment of inertia of the shapes that you had. So good luck, and go ahead and do some practice problems to make sure you understand this.